So welcome. So this is, I think, our second look at Gauss's law. What we discussed last time is that we have, it's a construction. We take the arrows that we imagine to represent electric field lines, and we basically recognize the fact that they are closer together. There's more of them per unit square meter where the field is high, and there's fewer of them per unit square meter where things are low. So we can devise this thing called flux, and it's basically electric field times the area. Big electric field gives you more flux per area. Small electric field gives you less flux per area. If we're at an angle, we learned how we could deal with that, and in fact we quickly got to the stage where we decided to think in terms of a area vector to represent area. So we have a field vector and we have an area vector, and we dot them. We do a dot product of them, and we know how to do that. And then we did a couple of examples, and I think we'd got to just about this stage where we started saying, well, hold on, let's say that we have a whole bunch of these Gaussian surfaces, these cards, and we make up a mosaic of them so that we can actually enclose a volume. So we have an electric field line, in this example, emerging from this volume, and the card that it emerges through has a certain area vector. So we can call that dA, the little bit of area, and the electric field line there. And we can say in a non-uniform electric field, that's where the arrows are diverging or converging. In a non-uniform electric field, our equation works for a sample element. So whereas before we had flux is equal to E dotted with A, now we're going to say, well, our flux works for E dotted with the little bit of area, dA, this little bit of area, the area of this little tile here. We define a vector, little dA, whose magnitude represents the area of this ith element of the surface. The direction of dA is perpendicular to the surface element, so it's always at 90 degrees. And here's the trick. What we said before is when you have a card, is the A vector in that direction or in that direction if I look at it from the side? And what you do is the A vector is always pointing outwards. So the little dAs are always pointing out. That's how we decide which direction to put the dAs in. They're always pointing outwards. The electric field are not always pointing outwards, but the little area vectors are always pointing outwards. And we can say, well, our little bit of flux is equal to our electric field times a little bit of area cosine the angle between, which is EI times dotted with the little bit of area vector. And we can find the overall effect by summing the contributions of all these surface elements. So we say, well, the total flux is the limit as my area bit goes to 0 of all these summations. So I get the integral of E dot dA, which is a surface integral. So I'm going to integrate over this entire surface. There's three possibilities when you think about it. Here I'm showing my electric field just going from left to right. And I drew three little bits of it. Remember, these electric field lines are just the direction that the field goes in. At any point, you can define an electric field vector, and that gives you the strength and the direction at that point. So it's kind of important not to get the electric field lines confused with the electric field vectors. The electric field lines just go in the direction that the positive charge would flow along. But at any point, we can say, well, what is the size and direction of the electric field? So if I had something like that, if my electric field went like that, I would have an electric field vector there, electric field vector there, electric field vector there, and electric field vector there. So don't get confused about the things we did in lab, which were the field lines, and when we draw a field vector. Yeah? So we picked a point here, and we said, there's its electric field, There's the electric field, and there's its electric field. They're parallel and the same length. It's a uniform electric field. But because we pick this Gaussian surface, in this case to be spherical, I'm just showing the edge of it. Our area vector always goes at 90 degrees to the surface, and it always points away from the body of the surface. It always points outwards. So we have three different situations here. We have one situation where the angle between the area vector and the electric field is less than 90. We have an example where it is 90, an example where it's more than 90. And because we're using because we're using it's a cosine function in the end, what we find is the sign depends upon what we have. We say the field lines are entering the surface. That would be this guy. When the field line is entering the surface, then our angle of theta is, well, basically it's going to be between 90 and, what's the most it could be? It could be 180. Don't know why that, oh, it's there. Between 90 and 180. And so cos theta is negative, and so the flux is negative. So for instance, you'd say this would be minus 0.69. So when the electric field is entering a Gaussian surface, we have negative flux. So this is neg flux. Okay. When would the, oh well, I've got to be careful here. Let's leave it at that. Okay, I'll talk about the way we set it up in a minute. If we take another situation where we just moved our region of interest, so our field, our area vector is at 90 degrees to our field vector, well, cosine of 90 equals 0. So our flux equals 0. So when the electric field is grazing the Gaussian surface, no flux. And if we have our electric field emerging from the Gaussian surface, then our theta is less than 90, which gives us a positive value. Yes?
Sir, forgive me, I'm trying to interpret here. So I noticed that the direction there is pointing away to the left, so that would basically denote it as being negative? Because the angle would basically dictate that
which direction are we talking about?
Right there was the dA, vector dA.
The vector dA.
Yes, it's pointing to the left. So would that basically denote?
No, we're in three-dimensional space, and so we don't have the positive-negative number line anymore. Okay, so I could have my electric field going in that direction and have everything reversed.
Yeah, it's still be negative.
Yeah. Well, if this thing was pointing in that direction, then that would be a positive flux. It's the angle between the electric field and the area vector. Okay? So when the angle is greater than 90, you get a negative flux. When it's less than 90, you get a positive flux. Okay? Okay, so when we say the net flux is simply the sum of all those guys, so you sum over the area vector. You sum over the area. Okay? Now, let's just stop for a minute and think. Boom. Let's say that I have, I'm going to go, no, I'm going to wait on this. Okay. So let's just derive Gauss's law. To derive Gauss's law, I'm going to imagine a very specific situation. I'm going to have a point charge, and I am going to construct, you construct the Gaussian surfaces. That's part of your task. I'm going to construct a Gaussian surface about this point charge, which is symmetrical about the point charge and is spherically symmetrical in this case. And I'm doing that for a couple of reasons. And one reason is that if I imagine this in cross-section, my electric fields are going to point away on a radius, and my area vectors are going to point away on a radius. And so for every piece of surface, the area vector and the electric field are going to be parallel to each other. And that just makes my math easier. So I'm picking a symmetry to make my math easier. Okay? I say there is general relationship between the net flux through the closed surface, the Gaussian surface, and the charge and the change in and the charge that it encloses. When electric field is parallel to dA, I can say E dot dA becomes the magnitude of E times the magnitude of the area. So if I say flux is equal to the surface integral of E dot dA, I get, well, my flux is equal to the integral of E dot dA, which equals, well, E's a constant on this surface. It's constant because I'm the same distance away. That 1 over r squared relationship doesn't matter because I'm the same distance away. So that's a constant. So let's take it outside our integral. So I have a constant E times the integral dA. And the integral of dA is simply the surface area of the sphere, because it's a spherical Gaussian surface. So I say, well, if I remember that the electric field near a point charge is KEQ over r squared, and if I remember that my area of a sphere is 4 pi r squared, if I take these two guys together, I say my flux, which is equal to the surface integral of E dot dA, which is, because E's constant for the diagram that I drew, it's E integral dA, which is KEQ over r squared, that's my E, and my integral dA is 4 pi r squared. I get, well, cancelling, I get 4 pi times KE times Q. Almost there. If I recall that my Coulomb's constant is 1 over 4 pi epsilon naught, I can say, oh, what that gives me is 4 pi Q, and instead of the KE put 1 over 4 pi epsilon naught. Yeah, pi's cancel, and we get Q over epsilon naught. So I get flux is equal to the surface integral of E dot dA, which equals Q in over epsilon naught. Now that is Gauss's law. What we're saying is that that's true. And you don't need to worry, frankly, about where it comes from. You do need to know it, though. So my flux through this surface is equal to the surface integral of E dot dA for this surface. And it equals the Q inside this surface divided by epsilon naught. Now, that's really interesting, because if I turn things around a bit, if I know the charge inside a surface, I have an immediate representation of the flux. The flux is equal to the charge inside in coulombs over epsilon naught. And if the flux represents the number of lines, arrows, that's kind of telling you how many arrows we're imagining. Too many to draw. It turns out there's a lot of arrows. Too many to draw, but that's how we get it. And then the other thing is, the charge over this constant is relatively simply linked to the electric field in the area. And so the game we're going to play with this is we're going to basically start using Gauss's law to determine the electric field. That's the game we're going to play. We're going to play a game where we're going to try and find the electric field near some charge distributions that we can't just find from a point source of charge. So there's only so many examples. I'm going to show you most of those examples. But let's step back for a minute and let's look at this Q in over epsilon naught and my flux. So here I've imagined a situation where I've drawn 3 positive charges and I put them inside a Gaussian surface. Remember, this is 3-dimensional. I'm only drawing 2 dimensions, but it's inside the Gaussian surface. And there's a radial distribution of charge going outwards. So my flux line, there's a radial field lines going outwards. And so I chose, it doesn't have to be a spherical Gaussian surface. I can do, in principle, any Gaussian surface I like as long as it's closed. And what I can say is that my net electric flux, that's the total amount, if you like, of arrows going into or out of my Gaussian surface, is basically, well, it's going to be flux is equal to the surface integral of E dot dA, which equals Q inside over epsilon naught, and my Q inside here is 3 positive, so it's plus 3 over epsilon naught. So if I say to you, what's the flux through that Gaussian surface? Look at the charge inside and say, so that charge over epsilon naught. Let's just move our Gaussian surface. So now there's no charge inside our Gaussian surface. And what this says is that the flux, that's the number of arrows entering or leaving our Gaussian surface, is equal to the charge inside, which is 0 over epsilon naught, which is 0. And if you look and say, well, there's one entering, but there's one leaving. And if I want to draw more arrows in, there's one entering and there's one leaving. There's one entering and there's one leaving. The net amount is 0. What's the flux through Gaussian surface 1? There's Gaussian surface 1 in the middle. Well, it would be Q1 over epsilon naught. What's the flux through Gaussian surface 2? Here's Gaussian surface 2. Well, it would be Q2 plus Q3 over epsilon naught. What's the Gaussian surface through 3? Well, there's no charge in there, so it would be 0 over epsilon naught, which is 0. Yeah? What would that be? That would be Q1 plus Q2 plus Q3 over epsilon naught newtons per coulomb meters squared. So it turns out that flux is actually pretty easy to work out for a closed Gaussian surface. Just the total amount of charge divided by epsilon naught. It's very nice. So a positive charge sits at the center of a spherical surface of radius 8 meters. So here's my 2 positive this is my Gaussian surface, and this is 8 meters radius. What's the electric flux? I say my flux is equal to the surface integral of E dotted with dA, which equals Q inside over epsilon naught. My flux is equal to, forget about the surface integral of E dA. I know the flux inside. I know the charge inside. So there's my answer. And again, that represents the kind of electric field arrows, how many electric field arrows you have leaving or entering, the net amount. Okay? A 5 coulomb negative charge sits at point. Oh, this is a bit more interesting. So it's giving me these IJKs. And what are these IJKs telling me? They're telling me where this charge is. Sits at. It's a position ijk, isn't it really? It says 1, 2, 1, 2, 1, 2. So it's there, isn't it? And it's 5 coulombs negative, 5 negative. That's where I'm at. That's just telling me where my position is. Then the next bit says a Gaussian surface is 4 meters on edge with one corner. A cubic Gaussian surface is 4 meters on edge with one corner at the origin. So there's one corner of it. Its opposite corner at 4, 4, 4. Well, it's a cube. So it's going to be 4 by 4 by 4. So there's my Gaussian surface. What is the flux? So what does my flux equal? Surface integral of V dotted with dA. And what does that equal? What does that equal? Look back at your equation. What does that equal?
Charge inside over epsilon.
Q inside over epsilon naught. So I've got to ask you a question. Is there any charge inside your Gaussian surface?
Negative charge.
Yeah, there is. This guy is inside, isn't it? So my flux is equal to minus 5 over epsilon naught newtons per coulomb meter squared. So all of that was about just being able to answer, is this charge inside or outside? Does it matter if it's in the middle? Absolutely not. As long as it's anywhere inside it. It can't be on the wall of it. It's got to be inside it. But if there's any charge inside it, it's great, yes.
Does it matter the material?
There's no material here. This is not a cube made out of anything. This is an imaginary cube. And that's so I'm glad you asked that question, because that's not obvious. You know, we're drawing these spheres and all that, and it's easy to get the idea that there is something there. It's just in my mind. I'm imagining putting that surface there. Yeah. Cool. So now let's turn it around a bit and use this. So we say, let's use Gauss's law to determine the electric field caused by a specific charge distribution. Here's how you do them. You say, look at the Gaussians, look for, that means draw, develop, look for Gaussian surfaces that have the following properties. You want the value of the electric field to be constant over the surface if you can. You don't want to be trying to figure out one E here and another E there and another E there. Just try and draw your surface so that it's a constant value. The dot product can be expressed as simple algebraic product because E is parallel to A. You'd like, if you have E always parallel to dA, then you don't need to worry about the angles. If they're diverging, if A is diverging from E, you've got to take that angle into account. So try and get them parallel. If not, pick another surface where the E is perpendicular to dA, because you know that's 0. It's in between that's the problem. The electric field can be argued to be 0. It's like you just got no electric field. You can make some argument about there's no electric field and then solve. So there's like 4 things that we kind of look for, and we're gonna go through those. Let me just give you the scope of things. We talk about a point charge and a point so far away from it. I can talk about a ball of charge and a point so far away from it. I can talk about a ball of charge and a point that's inside it. I can talk about a shell of charge and a point that's on the outside of it. I can talk about a shell of charge and a point that's inside it. So this is positives, and these guys are just filled with positives. And then these guys have positives on the outside, or negatives, whatever. And these guys are charges on the outside. I can talk about a plane of charge and a point that's to one side. I can talk about a line of charge and a point that's to one side. So those are the scenarios. This one's pretty straightforward. And we're learning from the rest. We know the answer to this one. The answer to this one is KEQ over R squared. We know the electric field is that. We know that one for that one. That's done. We're going to prove it again this way. But then we're going to try and generalize and learn these others. There's going to be a Gaussian surface on your test. There always is. What's the electric field due to a point charge? So here's a point charge, and we picked a point somewhere here. It's a certain distance away. We pick a spherical Gaussian surface centered on the point charge because A, for the surface, the electric field is parallel to dA. That's nice. And secondly, the electric field is always constant. Anywhere on this Gaussian surface, the electric field is constant. Yeah? So let's step through it. First thing, write down the law. Electric flux is equal to the surface integral of E dot dA, which equals Q in over epsilon naught. That's the law. Now let's apply the law to the Gaussian surface that we drew around this charge. And the first thing I can tell you is that E is constant on the Gaussian surface. And I would like you actually to write that down. E is constant on the Gaussian surface. So you know what you're doing. E is constant on that Gaussian surface. Why is E constant? Anybody tell me, why do I know that E is constant on that Gaussian surface?
Because it's spherical, and every point on that surface would be the same distance away from that.
That's the point. Every point on that surface is the same distance away from the charge. It's the 1 over R squared, but R's constant. Yes, and it turns out to be spherical for that. Yeah, yeah, go. Very good. So, okay. So I take my E outside my integral. And then I say, well, hold on. My E... Oh, and I've got another thing as well. I did two things in one here, and shame on me. E is parallel to dA. And what that does is it means that the surface integral of E dot dA, which equals E dA cosine the angle, can go to E times dA. Now it's the integral of all those. But can you see how, because these two are parallel, because E is parallel to dA, that goes to 1. Yeah? So this is the magnitude of E times the magnitude of dA, not the vectors. So I get rid of the vectors by saying E is parallel to dA and going from there. And then I get the E outside my integral by saying it's constant. So there's two steps there. And then I say, well, okay, E integral dA equals Q in over epsilon naught. Well, I know that my integral of dA, because it's a sphere, is 4 pi r squared. So I go, my flux is equal to E times 4 pi r squared equals the charge inside over epsilon naught. And then solving for E, that's what we want to isolate. So E is equal to Q in over 4 pi r squared times epsilon naught. Just take the 4 pi r squared to the other side. Last little bit. My Coulomb's constant is equal to 1 over 4 pi epsilon naught. There's 4 pi, there's epsilon naught. I can replace that with a Ke. So I get this equals Keq over r squared. There's my answer. That's what we worked out originally, wasn't it? That was what we got from Gauss's, from Coulomb's law. That was Coulomb's law, yeah? So to some extent, we're doing something that's a bit redundant here, but we're showing the methodology. Let's just do this. I want you to lead me. So we have a charge at the origin. And this charge is 10 Coulomb positive. Using the method of Gauss's law as shown in class, determine the electric field at a point 3 meters from the point charge. Let's just pick a point, just 3 meters. There's a point. It's 3 meters away. I happen to draw it on the x-axis. It does not matter. I can draw it anywhere I like. Now, the intellectual decision I've got to do is I've got to say, and what I want is I want to find that electric field. That's what I want to find. And the intellectual decision that I got to make is what kind of Gaussian surface do I draw? And I'm looking for a Gaussian surface where electric field is constant, and I'd like my electric field and my area vector to be parallel. And after a bit of practice, you realize, oh, point charge, go for the symmetry. So I'm going to do a spherical Gaussian surface. You go for the symmetry. And you say, oh, I'm going to imagine a little window here. There's my dA. I say my flux is equal to the surface integral of vector E dotted with vector dA, and that equals my Q inside over epsilon naught. And then I say, well, okay, my vector E is parallel to my vector dA. So my vector E is equal to the integral of E dA cosine theta, and that goes to 1 because they're parallel, which equals Q inside over epsilon. Then I say, well, E is constant on that Gaussian surface, so you don't need that. It's the magnitude of E. That E is constant. So my flux is equal to E times the integral of dA, which equals Q inside over epsilon. Then I say, well, my integral dA is equal to 4 pi r squared. So I can say my flux is equal to E times 4 pi r squared, which equals Q inside over epsilon naught. Then I say, well, in that case then, now forget about your flux. You don't need your flux anymore. E is equal to Q inside over 4 pi r squared times epsilon naught. And I say, well, Ke is equal to 1 over 4 pi epsilon naught. So E is equal to Q inside times Ke over R squared. So that would be Ke 9 times 10 to the 9 times my Q inside is plus 10 over R squared, and R squared was 3, so that's going to be 3 squared. 1 times 10 to the 10 newtons per coulomb meters squared. Can you see that? Stop that for a minute. So let's make this a bit more interesting. Rather than having a point charge, I'm going to stick all the charges together so I form a sphere. Not a hollow sphere. A sphere like, you know, what is it, one of those jawbreakers where you can suck all the way through. It's not got a hole in the middle. It's like completely filled with charge. How can I make it? That's a whole other issue. Don't worry about that. Now, it's a bit like the Earth, isn't it? The Earth has stuff inside it. It's a bit like the Earth. So the two possible questions I can ask is, well, was the electric field above the surface of the Earth? Or I could say, what's the electric field inside the surface of the Earth? In either case, I'm going to pick my point of interest above the surface of the Earth, or below the surface of the Earth, or outside the charge ball, or inside the charge ball, and I'm going to make sure my Gaussian surface goes through it. Clearly that's something that your Gaussian surface has to go through your point of interest, otherwise it don't work. Yeah? It's irrelevant if it doesn't go through the point of interest. So I'm going to put a Gaussian surface through my point of interest, and I'm going to look for symmetries that help. And even though this is not a point charge, even though this is a ball of charge, because it's a spherically symmetrical ball of charge, it's still very useful to have my spherically symmetrical Gaussian surface. Because, once again, every point on this Gaussian surface, the electric field is constant. And for any given little point, my dA is going to be parallel to my electric field. So it's going to work out, isn't it? You can guess by this first one that there's no real difference between the point of interest being outside a ball and the point of interest being outside a point charge, which has the same amount of charge as the ball, you know. But this looks very different. This looks complicated. So let's see where those come from. Using the method of Gauss's law that was shown in class, determine the electric field 2 meters from the center of a 4 meter Gaussian surface. From a 4 meter radius ball of charge. Oh, so now we've got to be a bit careful with our diagram. And I think here colors can help a lot. So I'm going to have my ball of charge, and my ball of charge is 4 meters radius, and Q is equal to 9 coulombs, and I'm assuming it's positive charge. Now I'm going to change colored pen so it's a bit more clear. Let's go to something like purple. I'm interested in the point that is 2 meters from the center, so my point of interest is there. That's 2 meters. Here's my point P. It's inside the charge distribution. I want to devise a Gaussian surface that will have all the symmetries going for it, but goes through point P. And it seems to me you've got some spherical symmetry here. So again, make a spherically symmetrical Gaussian surface. This imaginary Gaussian surface. Because then I get my E is again parallel to my dA. And my E is constant on that Gaussian surface. Even though it's inside the charge, it doesn't matter. And I say my flux is equal to the integral of vector E dotted with vector dA. And that's going to equal my charge inside my Gaussian surface over epsilon naught. I just want to look back for 1 minute because I want to get the letters right. Let's have a look. Boom, 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 boom. Yes. I'm going to call the radius, the distance from the center to my point of interest R. And I'm going to call the distance from the center to my charge A, just so I can use those letters. Okay? So now I can say that my flux, oops, I missed a step. So the first thing to realize is that E is parallel to dA for this Gaussian surface. I'm going to do that in green because I want to kind of emphasize, sorry, I'm going to do that in green because I want to kind of emphasize to you that I'm looking at the green bit. I want to emphasize that to you. So I'm going to say E is parallel to dA. So the integral of E dotted with dA is equal to E times dA times the cosine of the angle between, and that of course is cosine of 0, which is 1. So I can say my flux is equal to the integral of E dA, which equals Qn over epsilon naught. And the next thing I'm going to say is that E is constant on Gaussian surface. So my flux is equal to E, the integral of dA, which equals Qn over epsilon naught. Just took that E outside. And then I say, well, integral dA is equal to 4 pi, and the generic term is 4 pi r squared, but I'm talking about my Gaussian surface. And it is r, isn't it? Okay, that's okay. So that's 4 pi r squared. Yep. So I can say that my flux is equal to 4 pi r squared, E times 4 pi r squared, which equals Qn over epsilon naught. So I can say that E is equal to Qn over 4 pi r squared times epsilon naught. And I can go even one step further and say, well, Ke is equal to 1 over 4 pi epsilon naught. So E is equal to Q inside over, well, times Ke over r squared. Well, that's the same thing we had before. Except I'm not finished. Because I've got to be a little bit smart here. I'm trying to get a colour. Let's do black. Because my Q inside is not 9. That's for the entire ball. My Q inside is not the same as my Q. The Q is like the red sphere. So Q inside is equal to the little volume times the volume density. So Q inside is equal to 4/3 pi r cubed times the volume density of charge, of course, which is big Q over 4/3 pi. What's the radius of the charge?
2.
No, don't look at the numbers, look at your diagram. What's the radius of the charge?
4.
No. Give me a letter.
Oh,
A. A cubed. So this is going to equal the 4/3. Pi goes away. Q times r cubed over A cubed. So I get E is equal to KE Q r cubed over A cubed all over r squared. KEQ r over A cubed. Yep. So E is equal to, it's going to be, let's leave the KE alone. The Q is 9. The R, now you've got to be careful which way around this is now. So the R is to the Gaussian surface. So that's 2 over A cubed. That's 4 cubed. Which equals 18 over 4 4s are 16, 4 16s is 64 KE, which equals what? 2 9s are 18, 9 doesn't go into 64, so 9 over 32. There it is. So that's a typical test question. Okay. And what I'd look for is I'd look for, do you know Gauss's law? I'd look for, do you know that your area is 4 pi r squared? Can you substitute in for that? Can you take your E outside? These steps. I'd love to see that E is parallel to dA and that E is constant. You have to write down E is constant this time. And E is constant. I'd love to see those two. KE is equal to 1 over 4 pi epsilon naught. And then, of course, this bit down here is very important. It's the physics of it. It's like, you know, it's not the equation at the end. It's the physics of it.
Would you want us to plug in for Coulomb's constant?
No, not on a test. Got enough to do on a test. It looks complicated. The first time you see it, you kind of go, whoa, that's like crazy. But it's the same pattern all the time. So if I show you this next one, again, when you're outside, it's the same old equation. It doesn't matter about it's still KEQ over R squared. It's an inverse square relationship. But when you're inside, now this is 0. Now, can you see? Let's look back. We came along, we drew a Gaussian surface. Drew a Gaussian surface there as well. We came along, yada, 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 and we get to this point. It's the same old point, but again we recognize that the charge inside is not whatever the charge on the shell is. Because the charge inside is inside the Gaussian surface, and there's no charge inside that Gaussian surface. And can you see how, as if there's no charge inside that Gaussian surface, then Q goes to 0. So the answer is 0. Let's do a little bit of conceptualizing. Here's the Earth. Let's say we're working out the gravitational field. We could do the same thing with the gravitational field, by the way. It would work. According to this, outside the Earth, you have an inverse square law. That's what we see, don't we? We see an inverse square law. Inside, what kind of law is it? What kind of relationship is it? Is it inverse cubed or is it linear? Well, if you think about it, the thing your variable is r in both cases, yeah? Point of interest. So it's inverse square for this guy, but for this guy it's linear, yeah? A is a constant, yeah? So what does this look like if I plot a graph of electric field versus position, where that's my A, that's the radius of my charge. I get a nice linear relationship until I get to my charge. And then I get an inverse square afterwards. And the same goes for little g. If I do little g versus r for the Earth, I get inverse square relationship above the surface of the Earth, and inside the Earth I get a linear relationship. So what is the gravitational field strength at the middle of the Earth?
The middle?
Middle of the Earth.
Like 0?
0.
0, isn't it? You're not being pulled. You've been pulled equally in all directions. So it cancels out. So if you were to fall through the middle of the Earth, the pull of gravity on you would get less and less and less and less and less until you reach the middle. And then it would get more and more in the opposite direction until you got to the surface of the Earth. So it's kind of a complicated little pendulum, really. Look at this. What this is telling you is that for the electric field, we have inverse square once we're outside the shell of charge. But when we're in that gap, we have no electric field. Doesn't matter whether I'm close to the shell or far away from the shell. I could be way out here, could be here, could be here, could be here. It's 0 throughout. That would be like digging a hole through the earth and finding that it's only a shell. There's no core, there's no whatever. It's just a shell of matter. You can imagine opening a trapdoor and just diving inside. And you would be just no pull of gravity on you. You'd float around. If you were just inside, you'd just float around inside the shell of the earth. It's not like that, is it? But, you know, we don't think anyway. No one's ever done it. But, and no electric field inside. Well, that's pretty good. You want to protect yourself from electric forces? Go to a place with no electric field. So what they have in high voltage situations, often they'll have a cage. And the people operate their machines inside the cage. So this could be very high voltage machine here and here, like a Van de Graaff generator. It's like millions of volts. And you can control it if you're inside a cage of copper or metal, whatever, anything conducting. Because no matter what charge builds up on that, you can have lightning striking it. Whatever builds up on that, there's no electric field on the inside. No electric field, no force per charge. You don't feel it. You don't feel that electric force. It's really, so that's a Faraday's cage. That's a really nicely designed thing. How are we doing for time? Going to stop.